We begin our exploration of dynamic IPv6 routing protocols with a look at RIP Next Generation. Ah yes, RIP, not going away anytime soon. RIP Next Generation is really similar to RIP version 2 for IPv4. For example, we know that an improvement in RIP version 2 for v4 was the fact that RIP would multicast its routing updates as opposed to broadcasting them. And RIP Next Generation, or IPv6 RIP, is certainly no exception to that. It will be multicasting updates to FF02::9. Notice how similar this is to the v4 address of 224.0.0.9 that RIP version 2 utilizes for its updates. RIP Next Generation, if you want to read the official standards document, is available in RFC 2080, which is going to completely detail this particular protocol for you. What we want to spend our time doing in this video on demand is taking a look at a sample configuration. And to make this a bit more interesting, we'll take a look at a RIP over frame relay type configuration. Notice we have a classic hub and spoke type of topology here, with R1 acting as headquarters and R2 and R3 acting as branch offices. We will configure RIP, IPv6 RIP in this topology, and we will be done when we can achieve full connectivity. Of particular interest will be the loopback 103 network off of R3. So when everyone can reach that particular destination, we'll know that we have achieved full connectivity with IPv6 RIP. The big commands that we'll be seeing in this particular video on demand will include frame relay map IPv6, a command that is going to be needed throughout this topology, and we'll take a look at the IPv6 RIP, and then in our case a tag of CCIE RIP enable. This command will enable RIP under particular interfaces. Those are really the two big commands that will be featured in this video on demand. Well, let's get started with this configuration. Let's go ahead and begin on R1. I'm going to go ahead and go right to that serial interface and get started with the configuration there. First of all, we obviously want to set the encapsulation to frame relay, and I have done nothing really in advance, so we're going to make this configuration of IPv6 RIP from scratch. The only thing we've done in advance is we've set up the frame relay switch to accommodate this environment. So I'm going to set encapsulation frame on the serial 0 interface of R1. Then I'm going to go ahead and assign our IPv6 address, and that is 2001::1/64. So we've got our v6 address set up. Now I'm going to go ahead and take care of my frame relay mappings. These are going to be v6 maps. So it's frame relay map IPv6, and I am going to map 2001:12:3 to Delcy 103. I'm not going to bother with the broadcast keyword yet on this circuit, and we'll see why in a moment. So there's a mapping for the global unicast address on R3. And then we're going to do a mapping for the global unicast address on R2. And that is out Delcy 102. So there are our mappings for the global unicast addresses on R2 and R3 respectively on R1. And we're done for now with the configuration. This might be a good point at which to save. Okay, let's go over to R2, and we are going to say encap frame under the serial 0 interface, we'll assign the IPv6 address of 2001:2/64. Very good idea to check your typing on these IPv6 addresses. Obviously, area here where you could be prone to a typo. Frame relay map IPv6, and we're going to create the mapping back to headquarters. Out Delcy 201. Again, I will not bother with the broadcast keyword. Now we have finished the mapping from R1 to R2, so we can go ahead and test at this point. We should be able to, from R2, we should be able to ping the headquarters global unicast address. And we can. So we have completed and verified the basic circuit between R1 and R2. Good time to save our configuration on R2 and move over to R3. On R3, we will enter interface configuration mode. We'll say encap frame. We'll say frame map IPv6. And we'll say 2001:12:1 out circuit 301. I won't bother with the broadcast keyword yet. We'll end our configuration, and we'll do a ping test from R3 to R1. Ping 2001:12:1, and we are not successful there. Notice the error message in this case. The ping wasn't even really attempted. We instead get the message unrecognized host or address or protocol not running. Aha, protocol not running. What have we forgotten here? Well, under the interface serial 0, we neglected to add an IP address, an IPv6 address. Okay, good catch. IPv6 address 2001:12:3/64. Now that we have an IPv6 address on that interface, now we can redo our ping to headquarters, and we see it succeeds just fine. Let's save our configuration right there, and we'll move on to our next step. So we have set up the basic V6 connectivity between R1 and R2 and R1 and R3. But that's not our goal. Our goal is to get full reachability to all of these particular entities. We want R2 to be able to reach R3 and vice versa, R3 to be able to reach R2. And, by the way, this additional network must offer full reachability. Let's go create that network right now. That's interface loopback 103, and its IPv6 address 2001:33:3/64. And we'll wait to make sure that loopback interface is in the up state. In fact, why wait? Let's do a show IPv6 interface brief. And yes, there is our loopback 103 interface, and it is in the up status. Okay, now what I'm going to take care of next is the frame relay maps for the link local addresses. You realize that when we created these IPv6 addresses on each of these interfaces, there was a link local address created. As a matter of fact, I can see the link local address right here for R3. There is the link local address that was automatically created for us on R3. We need to provide frame relay mappings for these link local addresses as well. Why in the world do we need to do that? Well, because RIP Next Generation, or IPv6 RIP, is going to use this link local address as the next hop. So because RIP is going to use link local addressing for the next hop, we need to create frame relay mappings to these link local addresses so that routing can succeed over the frame relay environment. There's many different ways you could approach this. I believe what I'll do is I'll go ahead and let me go ahead and pull up Notepad for a moment so we can see it. One moment. Okay, I've just launched Notepad, one of the tools that you are going to be provided with in the CCIE lab, by the way. And what I'm going to do right now is I'm going to go ahead and I'm going to grab this address. I'm going to go ahead and copy this address, this link local address, and I'll go ahead and I'll just say R3, and I'll paste that into Notepad. And now let me go ahead and skip over to R2. And on R2 I'll say show IPv6 interface brief. And I will grab the link local address, I'll copy it, and we'll paste that into Notepad. That is for R2. Alright, and finally, let's go ahead and do a show IPv6 interface serial 0, and let's grab the link local address, another way to get it, and this one is of course for R1. And let's paste that into Notepad. So I'm using Notepad here just to kind of help me document my network, specifically the link local addresses. Could you have assigned link local addresses yourself? Yes, you could have, but I just prefer to go ahead and grab the ones that were automatically created by the operating system. Alright, well here on R1, let's go ahead and let's go into interface serial 0, and let's say frame map IPv6, and I'll go to Notepad, and I'll say, okay, let's grab the mapping for R2, and let's paste it in. So this is for R2, so it'll be once again out circuit 102, and now we'll say broadcast. So broadcast will be permitted on that circuit. This is important because we know that RIP Next Generation multicasts its traffic. And now one for R3. Again, I'll just go to Notepad. I will copy. I'll come over here. I'll say frame map IPv6. We'll paste the appropriate address in. And this is going to be for R3 out 103. And again, broadcast will now be permitted on this circuit. Perfect. We'll go ahead and end that configuration. We'll go over to R2. Interface serial 0. Frame map IPv6, and on R2 we need the R1 link local. And that will be out Delcy 201, and we'll permit broadcast this time. So there's the configuration on R2, and finally R3. Interface serial 0, frame map IPv6. We've still got it in the clipboard, so I'll just do a paste. That'll be out Delcy 301, and we'll permit broadcasts. Lots of places that you could make a mistake here. So we're going to go carefully, step by step, and build this one step at a time. Now, we're ready, I think, for our RIPv6 configuration. We've got these circuits built, and we have now added frame relay mappings for the link local addresses. So we're ready for really the easiest part, and that's the RIP configuration. On R1, we can't forget this, IPv6 unicast routing. I should have mentioned this command is one of the ones we'd be showcasing. IPv6 unicast routing. That is our first required command here for RIP Next Generation. Now what we'll do is, under the serial interface, we will turn on RIP. IPv6 RIP CCIE RIP is the tag that we want to use, and then we say enable. That is how we can, in one step, enable the protocol on the interface and create the appropriate global configuration command. If you look in the running configuration, if I say show run include IPv6, you'll see a global configuration command was automatically added for us that simply said IPv6 router RIP CCIE RIP. This global configuration process command was created automatically for me by going under the interface and issuing the IPv6 RIP CCIE RIP enable command. So we got two things done there with one step. Alright, so we've enabled RIP on this R1 device on the serial 0 interface. I'll go ahead and save there. I'll go over to R2 and I'll do the same thing. I'll say IPv6 unicast routing, and then I'll say interface serial 0 IPv6 RIP CCIE RIP enable. In fact, we should do ourselves a favor and we should take this command and we should put it on the clipboard. So I'll do a copy. We don't want any typos with that command. I'll end, I'll save my configuration on R2, and R3 is the last one left to go. I'll say IPv6 unicast routing. I'll then say interface serial 0. I will paste in the command. And we want one more interface to be RIP enabled, don't we? And that interface would be interface loopback 103. And then we'll paste in the RIP enable command. Alright, we are in good shape. Now, let's go ahead and end and save there. Let's go over to R2 and let's start doing some verifications. First of all, in a v4 environment, I might do show IP protocols. Here I can do show IPv6 protocols. And here we see, okay, good. We're running routing protocols for connected routes, for static routes, and for RIP with the tag CCIE RIP. And on this particular router, the serial 0 interface is participating in these IPv6 routing protocols. Hey, I remember in v4 we had debug IP RIP. I wonder if we have debug IPv6 RIP. And look at that, we do. So we have debug IPv6 RIP, and I should be able to sit here on R2 and watch the periodic multicast updates sent and received, this time for RIP next generation. And we can just sit here and watch these periodic sending and receiving of multicasts. Now, what I want to do is to ensure this actually worked now. Do we have full reachability? And I think you'll agree with me that all we need to do to ensure full reachability is from R2 ping this loopback network down here on R3. If we can ping this network down here on R3, then we're definitely good to go. Now, to see if this ping would work, I'll do a show IPv6 route, and then I'll specify RIP. And this is a problem. This could be, in the exam for you, a real moment of panic. In your routing table, the RIP routing table, we do not have an entry for this 103 loopback interface. This could be a moment of panic for you if you weren't doing your training with us and you weren't walking through these scenarios. This is something fairly straightforward. Look at what's going on here. We have this hub and spoke frame relay topology, and what has bitten us here is, I believe, it should be, unless I've made a configuration error, but it should be, what I expect is the problem, is split horizon. We have this update coming in from R3 about this network into the serial 0 interface, and R1 doesn't want to send that update out the same interface. That is, of course, the loop prevention mechanism known as split horizon, and this is a feature of distance vector routing protocols, of which RIP Next Generation certainly is a member. So I think we can fix our reachability problem by going to R1 and saying IPv6 router CCIE RIP and going into the routing process. Let's see, what did I mess up there? IPv6 router RIP try. IPv6 router RIP CCIE RIP. Going into the global routing process and saying no split horizon. So let's turn off split horizon on R1 and see if that fixed our reachability issue. I'll reissue the show IPv6 route RIP command on R2. And look at that. No convergence delay here. It didn't look like much of one at all. Magically, our route now shows up. So turning off split horizon was necessary in this v6 RIP configuration. Let's go ahead and complete this illustration by pinging the loopback interface on R3. And I'm having a really good feeling about this. I think you should too. We'll ping 2001:33:3. And let's see if we have our full reachability. And we do not. So we do have an issue to further troubleshoot here. Now, we were looking for, let's check the routing table entry, 2001:33/64, going to the next hop of R1. Let's see if we can ping the serial 0 interface of R3. We should be able to do that. And we can't do that either. So we definitely have an issue here with R2's reachability to R3. Alrighty, let's check the interface configuration. I'll say show run interface serial 0. So we're checking our configuration here of the serial 0 interface, line by line. Encapsulation frame relay, IPv6 address 2001:12:2, CCIE RIP enable, perfect, and then our frame relay map statements. Those look great. Let's check connectivity to these addresses. Let's do a copy paste. That's perfect. Now when this happens to you in the exam, it can be very stressful obviously because the clock is ticking. So you want to do this troubleshooting as quickly as possible and quickly and efficiently as possible. The output interface here will be serial 0. It's not going to let me do that, is it? I probably need to spell it out. Okay, good. So we verified R2 is fine to the link local and the global unicast to R1. So things look good here. I'll go ahead and save my config on R2 and let's go over to R1, show run interface serial 0, and let's check out the work we did here. Don't see any problems here. Oh! No, that looks good. We have the link local and the global unicast, the global unicast and the link local. So those look good. Let's save the configuration there. And let's check R3. Show run interface serial 0. Checking these frame relay map statements. Let's ping these addresses. Okay, good. This ping I think we already tried and it worked, but we'll try it again, just in case. That works fine. We don't have mappings for the global unicast addresses, do we? In other words, R3 doesn't have a mapping to get to R2, and R2 doesn't have a mapping to get to R3. Frame map, IPv6, 2001, 12, 2, out Delcy 301. And on R2, interface serial 0, frame map, IPv6, 2001, 12, 3, out Delcy 201. On R2, let's try the ping again. The ping for full reachability, which would be 2001, colon 33, colon 3, and success. So, wow, we were just missing a couple of necessary frame relay map statements. One to get from R2 all the way over to R3, the other to get from R3 all the way over to R2, and that fixed our reachability. Let's look at the final configuration on the interface of R2. We see that we enabled RIP, and then we ended up with 3 mappings that were required. One to get to the global unicast IPv6 address on R1, one to get to the global unicast IPv6 address on R3, and then one for the link local address to make sure RIP would successfully run in this environment. So that was neat. We get to see a look at some troubleshooting and how I approach that. We can't panic. There's no need for panic when we're troubleshooting a configuration like this. Just go step by step logically, take a look at the running configurations, and think, what might be missing? What might we have missed? And in this case, a couple of important IPv6 frame relay map statements. Hope you've enjoyed this presentation on IPv6 RIP, and we'll be exploring other dynamic routing protocols for IPv6 in subsequent video on demands. I have been waiting for this VOD for a long time. I've been very excited to record it. We're going to look at OSPF version 3. Now, I've been so excited about this because OSPF is one of my all-time favorite protocols, and version 3 for IPv6 is going to be no exception to that. By the way, because I've been so excited about this VOD, I have not consumed any coffee within the last 48 hours because my excitement levels combined with caffeine would make for a very interesting video on demand for sure. So let's get started. First of all, I wanted to stress just how similar version 3 is to version 2 of OSPF. So please breathe a sigh of relief if you've got a lot of anxiety about this topic. If you've mastered OSPF version 2, and I'm sure you have with our video on demand products for that, you're definitely going to feel right at ease with version 3. Notice that this version 3 can run concurrently right alongside of the version 2 product. So that's great. The two are going to use separate shortest path first calculations, so there's not going to be any problem with running them side by side. We have the same basic packet types that we have with version 2 here in version 3. So our hello packets, our database description packets, our update packets, those are going to be the same types of things. Identical neighbor discovery and adjacency formation practices. You know the network types that you mastered with version 2, like point-to-point and NBMA and point-to-multipoint and point-to-multipoint non-broadcast and loopback and broadcast network type? All of those are here in version 3. So you'll feel right at home with network types as well. And we'll prove that at the command line here in a moment. LSA flooding and aging mechanisms, identical. So you might ask, my goodness, are there any differences? Well, certainly there are going to be differences. And a big one that shouldn't surprise you if you've played with the other IPv6 routing protocols is the fact that OSPF is going to use link local addressing for its adjacencies. Now think about that. It's using link local addresses for adjacencies. That opens up a couple of different facts. We can have multiple IPv6 subnets on a single link now. And also, we could have two nodes, and this sounds strange to us, but listen, we could have two nodes communicating over a link even if they're not in the same subnet. Imagine that. So with the link local addressing used for the adjacencies, the subnets of the global unicast addressing, they wouldn't even have to match, and we could still have communications possible. Well, I'm sure you're as excited as I am to get to the command line and to see some configuration of OSPF version 3, and let's do that right now. We've created, as you can see, a pretty simple but still multi-area topology. Let's go ahead and build area 0, and then, just like in version 2, let's have some different areas that touch area 0. By the way, we still have that core requirement in OSPF for connectivity to the backbone, or area 0. By the way, if you have a discontiguous area 0, or if you have an area that is not touching area 0, virtual links can be utilized in OSPF version 3, just as they could be in OSPF version 2. And of course, anytime I mention a virtual link, I have to point out that it is certainly not something that we are going to seek out to do by design. A virtual link is more of a band-aid for a temporary problem that we might have in our design. Why is it that we might see virtual links in the CCIE lab? Well, remember, in the CCIE lab environment, they're not giving you a well-designed, you're not building a well-designed network. You're building a network that is going to have everything and the kitchen sink included. All right, well, let's go ahead and get started here. Why don't we start at R1? That seems logical. Now, what I did behind the scenes was, I didn't think at this point you'd be interested in seeing me put on v6 addresses on these devices. So all I did behind the scenes was put the addressing in place, and I tested connectivity on each of these serial links. So we have the addressing in place, and it works. I've tested it. Okay. Now, on R1, let's start our configuration. Now, in OSPF version 3, we go to the interfaces to enable OSPF. We enable it on an interface-by-interface basis. For those of you familiar with ISIS, that's how we do it in ISIS. Also, for those of you familiar with late versions of OSPF version 2, you can actually go in and configure it under the interface. I think that showed up somewhere around 12.3 of the iOS. We could go in and start enabling OSPF on an interface-by-interface basis, as opposed to using the network command. No more network command in late versions of V3. If you want to V2, if you want to eliminate it, you can. In V3, there is definitely no use of the network command. Let's go ahead on R1 here and enter the interface serial 1/0, and let's try the command to enable OSPF on this interface. IPv6 OSPF, and we use a process ID. I'll just go ahead and pick a process ID of 1, and then we say area 0. Oh, we forgot something. Before we can play with OSPF on these routers, we need that very important global configuration command, IPv6 unicast routing. Remember, without this command, our R1 would be like a IPv6 host, not an IPv6 router. Now we can do routing. So let's get back into the serial 1/0 interface, And let's go ahead and try that command again. Great. Uh-oh. Looks like we're meeting with another error message here. OSPFv3 process 1 could not pick a router ID. Please configure manually. What in the world's going on here? How come it can't come up with a router ID? Well, the deal is OSPF version 3 is going to use a 32-bit router ID still. And what's happening here on R1 is it is looking for a 32-bit address to use as the router ID, and there isn't one. Oh my goodness. So it's telling us, look, I've got no 32-bit address with which to give you a router ID. You either need to create one or go off and configure the router ID manually. All right, great. I like configuring the router ID manually anyways, so I'll do that. I'm going to say IPv6 router OSPF1, and we're going to go into the global OSPF routing process. And I'll say router ID, and now watch what Bruce Caslow here at Netmaster Class taught me to do as far as this router ID goes. I love it. He wants me to go 0001, for instance. Why am I setting the router ID like that? That's a invalid 32-bit IP address. That's the whole point. Whenever I see this router ID, I want to be able to immediately recognize it's for OSPF version 3 on the router. So we go ahead and we set the router ID that way so we have distinction between a V2, OSPF version 2 router ID. Clever, clever idea. And here I just picked my router number, router 1. All right, now I think we're ready. Let's go ahead and go to interface serial 1/0 again. And let's once again try our command to enable OSPF for area 0 on that interface. And great, we meet with no error. So we'll go ahead and jump over now. I'm going to configure this just like I would configure it in the lab exam. Now, I actually take that back. In the lab exam, what I would probably do is I would probably configure both my interfaces on R1 to save time. And so I'd get all the R1 work done. But here, what I want to do is do it more like it would be in production. In production, what I would probably do is go over to R2 and configure that interface and test our area 0. As a matter of fact, a lot of people would do it that way in the lab exam. I might even do it that way in the lab exam myself. It all depends on what mood I was in, I guess. Both very valid approaches. I'm going to run over to R2 here, and I am going to say IPv6 unicast routing. We certainly don't want to get any error messages this time. I'm having some typos here. Let's try it again. IPv6 unicast routing. Excellent. I'll say IPv6 router OSPF1, and we'll say router ID 0002. Alrighty, I'll go into the serial 1/0 interface, and I'll say IPv6 OSPF1 area 0. Oh, that is exactly what we want to see. And I don't know, folks, what you think, but I think we have a much faster convergence here with version 3. Did you notice how quickly we went to the loading to full state on this particular router? Look at that. That is a great verification right there that our configuration is successful thus far. If you are paranoid, if you don't trust that, this is obviously a good time to do show IPv6 OSPF neighbor. This is almost identical. Notice again here this recurring theme. The IPv6 commands are almost identical to the version 4 commands. All you do is substitute IPv6 for IP and you're good. And look at this command output. It looks exactly like what we're used to from OSPF version 2. Look at that router ID. Boy, does that look strange. Got to post that on the internet and see if people can tell me what's up with that. Okay, this is great stuff. By the way, just to prove the similarities again, let me do a show IPv6 interface serial 1/0, And this output looks very familiar to us. That's not the command I wanted to run. Try this. Show IPv6 OSPF interface serial 1/0. This is the command I wanted to see. And notice it looks very similar in structure to the previous command. And what I wanted to point out here was, sure enough, on this serial interface running HDLC, it correctly set the network type for me of point-to-point. And the hello, dead, wait times, they are exactly as they would be in a version 2 OSPF environment. So we're very, very comfortable at this point so far with OSPF version 3. Okay, so our area 0 is intact. It looks good. We're on R2. We might as well start building area 24. Let me go ahead and say interface serial 1/1. And I'm going to say IPv6 OSPF1 area 24. We're done on R2. We're going to go over to R4. Oh, we got lots of work to do there. IPv6 unicast routing. Then IPv6 router OSPF1 router ID 0.0.0.4. And then interface serial 1/0 IPv6 OSPF1 area 24. How do you get good with these commands? Practice, 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 and these commands will become second nature to you. There is our status message indicating we're in the full state. I will go ahead and trust that status message at this point. And by the way, something that would be great to verify now would be your routing table. Shouldn't R4 know about the 12 link up here? It should via OSPF. Let's do a show IPv6 route OSPF. And look at this. It does indeed know about the 12 network, and it is correctly classified as an inter-area route. It's an inter-area route. That would be an LSA type of 3. So we have an LSA 3 here in the database, on the forwarding database on R4. Pretty neat. An inter-area route, just as we would expect. All right, one last router to configure. Let's go over to R3, and let's do the IPv6 unicast routing. We'll do the IPv6 router OSPF1 router ID 0.0.0.3. And then we'll say interface serial 1/0 IPv6 OSPF1 area 13. You know what we didn't do? I don't believe yet on R1 I've configured the interface in the appropriate area, so let's do that now. Interface. See, when you're doing things logically like this, you can catch mistakes like that, or you can catch issues like that just as you're configuring. IPv6. The important thing is to have an approach to the configuration. All right, IPv6 OSPF1 area 13. And we should get a status message. There it is. Great, our neighborship is up. We can test full connectivity now. Let me go ahead and ping 24:24:4. We are pinging, whoops, I'm on the wrong router for this. Let's do it from R3. So from R3, we want to ping all the way over to R4. Ping 24:24:4. Oh, we're in great shape. Look at this. Full unicast connectivity. R3 pinging all the way over to R4 in this OSPF environment. Well, we've got a few minutes left here in this VOD. Let's have a little bit more fun. One of the things that we love about OSPF, of course, is the different types of areas that we can create to increase the scalability and the efficiency of this routing protocol. Why don't we make Area 13, it's a rather dubious name, why don't we make it totally stubby? Right now, if we look at the routing table over here, show IPv6 route OSPF, whoops, show IPv6 route OSPF, we see we're starting to build, obviously, inter-area routes, LSA type 3s, for the network. Those will just build up here as we add more areas. If this is a stub type architecture, let's go ahead and make it totally stubby to increase the efficiency. How would we make an area totally stubby in OSPF version 2? Well, we'd go and we'd use the area stub no summary command on the area border router. That's exactly what we do here, folks. I'm going to go into router 1's OSPF configuration, IPv6 router OSPF1, and I'm going to say area 13 stub no summary. Folks, do you realize that is the exact same command I would have used in OSPF version 2? On the ABR, I would use that command. Oh, the adjacency was forced to reset. Yeah, there's a stub flag mismatch now. So we don't have an adjacency anymore between R1 and R3, and we expect that. We go over to R3 now, and we say IPv6 router OSPF1, and we're going to say area 13 stub. We do not need to say no summary on area 3. On router 3. We only need the no summary keyword on the area border router. A lot of people don't realize that. When I'm grading configurations and I see the no summary down here, it'll still work, but it just shows me that the person might not completely understand that command syntax. Our adjacency just came back up. This is a good sign. Now the ultimate test. If we look at the routing table of this totally stubby router, we should see it is much more efficient. Show IPv6 route OSPF. And how's that? We have one inter-area route now, and it is a default route. And that single default route will get us anywhere in our topology. Let's ping all the way over to R4 again. This time we'll go via the default static route there, and we still have great connectivity, and we have just created a totally stubby area. And for those of you fans of OSPF version 2, you're loving this because you have similar tools that are configured, in this case, in an identical way. And these tools in your tool belt you can utilize fully for your IPv6 configurations. Well, as always, everyone, thank you so much for attending this video on demand on OSPF version 3. And I can't wait to see you, I put that in quotes, in upcoming video on demands. It's time now for us to examine EIGRP for IPv6. And again, we're going to be very comfortable with many of the commands used in this video on demand if we've mastered EIGRP for IPv4. Let's take a look at some of the characteristics and requirements, however, of EIGRP for v6. There are going to be some unique things about the configuration of this protocol we need to be ready for. First of all, just like OSPF, this can run side by side or right on top of IPv4 EIGRP. Just like with OSPF, there's going to be a per interface configuration done here, and there is no use of the network command in EIGRP for v6. You know, it is interesting that they're phasing the network command out with protocols. I think they've always wanted to do this, and they being Cisco, because there's a lot of confusion between the network protocol as it's used with interior gateway protocols and the network command as it is used with exterior gateway protocols, specifically BGP. A lot of confusion is out there because the network command works one way with BGP and it has a different characteristic to it when you use it with an IGP. So I think they're trying to get rid of this command altogether from IGPs to avoid the confusion. With EIGRP v6, we use link local addressing once again for the adjacencies. This brings up the very interesting configuration where we can have EIGRP routers become adjacent even if they do not have global unicast addresses assigned. A router ID is going to be required for the configuration here. We'll show you what can happen if you don't have one. And also there's a shutdown feature for the routing process. And as we'll see, it's quite interesting. The routing protocol is going to start in the shutdown state. That could be a gotcha in the CCIE lab exam environment if you weren't prepared for it. Now, EIGRP version 4, we know it acted, or EIGRP for IPv4, I should say, we know it acted in a classful manner by default when it came to summarization. It did an auto summarization feature, and we do not have to worry about that in IPv6 EIGRP, as we will see. Well, I'm sure you're excited like I am to get to the command line with this protocol, so let's do it. Here's a configuration that we are going to build. Let's ensure we have universal connectivity in this configuration, and let's ensure that we can implement several of the EIGRP features. We'll implement the features primarily to show how this protocol is so much like its predecessor protocol. By the way, what I have done in the background in preparation for this video on demand, I went ahead and I put all of the v6 addressing in place and tested connectivity. So we're all addressed and now we're ready for the protocol. Let's go to R1 and let's configure EIGRP for IPv6. I'm going to begin by indicating, well, let's go to an interface and turn it on and see what happens. I'll go to serial 0/0/1. And I will say IPv6 EIGRP, and we'll set an autonomous system number here of 100. Aha! First thing I forgot was to enable unicast routing for IPv6 on this device. So I'll say IPv6 unicast, and we just turned on unicast routing. The full command, by the way, I should have mentioned was IPv6 unicast-routing is the full command. Okay. Let's see if that's going to get it done. I'll get back into the interface and I will rerun the IPv6 EIGRP 100 command. Okay, this time it seemed to work. Let's go over and let's configure the fast Ethernet interface. It needs to be enabled for EIGRP AS100, and let's end the configuration. Let's go down to R3 now and make the configuration on R3, and then we'll see if we can establish our adjacencies. So I'm going to say IPv6 unicast-routing, and I'm going to say interface fast Ethernet 0/0, and I'm going to say IPv6 EIGRP 100. Alrighty. Oh, by the way, we've got some loopback interfaces down here. We want to get EIGRP running on those. So let me say interface loopback, it's 301. And let me issue the appropriate EIGRP command. Interface loopback 302. And again, our appropriate EIGRP command. And interface loopback 303. By the way, I am starting to become troubled here. Why am I troubled? Well, because we have enabled EIGRP AS100 on the fast Ethernet 0/0 interface, and nothing has happened by way of an adjacency with R1. So I think we have problems. Let's go ahead and explore this a little bit. Let me do a show IPv6 EIGRP neighbors to ensure we don't have an adjacency. Aha! And we've discovered our first problem. The routing process starts in the shutdown state. Aha, so to actually enable this protocol, I've got to go and say IPv6 router EIGRP 100. Notice we are entering the routing process, and I've got to say no shutdown. Okay, now let's see if we get an adjacency. Not looking good so far. Let me do a show IPv6 EIGRP neighbor. Okay, and now we got another problem. No router ID. I sure wish we got console messages like we did in OSPF about these configuration errors, but they have not implemented those messages yet. Alrighty, we'll say IPv6 router EIGRP 100, and I'll say router ID 0.0.0.3. We will make this look like a v6 router ID by using that incompatible or that inappropriate v4 looking address. It's perfect. All right, so this is router ID 3. And by the way, we should be okay now on this router. I need to go up to R1, and I need to make the appropriate changes there. IPv6 router EIGRP 100. Router ID will be 0.0.0.1. And I'll say no shutdown. And now, whoops. Once I say no shutdown properly, IPv6 router EIGRP 100, we should see an adjacency establish. We've got our router ID, we have enabled the process, and we should see an adjacency. Let me do a show IPv6 EIGRP neighbor, and no neighborship yet. Let me do a show run fast Ethernet 0/0, show run interface fast Ethernet 0/0, and yes, we do indeed have EIGRP for AS100 enabled on the fast Ethernet 0/0 interface. Let me ping the other side. Ping, it would be 13.3. No valid source address for destination. We are getting this error because the interface either doesn't have IPv6 enabled on it, or, look at this, it's in the shutdown state. Okay, good troubleshooting there. Interface fast Ethernet 0/0, no shut. Okay, I'm hoping we see an adjacency established now. The interface just came up. And I think we better check the R3 fast Ethernet interface. Let's make sure it is in the up state. Show IP interface brief will do it. And sure enough, we're administratively down. I said I assigned interfaces with addresses. I didn't say I no shut those interfaces, though. All right, are we going to get an adjacency? The interfaces come up, and there's our adjacency. Fantastic. Okay, let's do some quick verification here. On R1, let me go ahead and do a show IPv6 route EIGRP. Excellent. We see the 3.1, the 3.2, and the 3.3 networks as learned by EIGRP. Fantastic. Okay, let's go over to R2 and quickly configure R2. At least I hope it'll be quick. We've learned a lot here about how to properly configure EIGRP. It should go pretty quick. IPv6 unicast routing. Oh, by the way, when we looked at the routes on R1, we saw the specific routes. Notice the no auto summarization. There is no longer any automatic summarization done, and most of us think that's a good thing. Alrighty, let's say IPv6 router EIGRP 100. Router ID will be 0.0.0.2, and we'll say no shutdown. Interface serial 0/0/1 IPv6 EIGRP 100, and interface fast Ethernet 0/0 IPv6 EIGRP 100, and we better do a no shut there. Okay, let's sit back, relax, and see if we get an adjacency. We should get an adjacency form between R1 and R2 as long as the interfaces are enabled. And they are the serial 0/0/1 is not. Okay, interface serial 0/0/1, no shut. And we better go over and do a no shut on R1. Oh, no need to. It was in the upstate because there is our adjacency. Perfect. So we're adjacent now between R1 and R2. Finally, R4. IPv6 unicast routing. IPv6 router EIGRP 100, router ID 0.0.0.4, no shut, interface fast Ethernet 0/0, no shut, IPv6 EIGRP 100, end, and sit back and wait for our adjacency, and there is our adjacency. Perfect. If we do a show IPv6 route EIGRP, we'll have full routing information, including these three networks over here. Excellent. And by the way, we could look at the topology database just like we could before. Show IPv6 EIGRP topology. And there's our topology database. We see our routes are nicely in the passive state. What about features? Well, folks, just take advantage of the features like you used to before. For instance, if we want to do some summarization here, I can go to R3 and I can say interface fast Ethernet 0/0, IPv6 summary address EIGRP 100, and I could say, oh, let's summarize on a 16-bit network address. And I did 13. That doesn't make any sense. Let me try that again. Interface fast Ethernet 0/0. We'll say no, and we'll remove this command. And we'll put in the correct summary. Always look for mistakes in your configuration as you're configuring. IPv6 summary address EIGRP 100, and it's 3 that I want to summarize for all of these 3 loopbacks. All right. The adjacency will come up and down as a result of that configuration change. Let's go over to R4 and do a show route and see if we have the summary. And we do. Perfect. So summarization, easy to do, and a simple interface configuration command does it just like before. Let's do one more feature. What do you say? Let's go ahead and go to R4 and configure R4's stub, the EIGRP stub feature. How did this work before? Well, we'd go into the routing process. So I'll go into EIGRP 100, and we'd say stub, and then we had options as far as what we were advertising. I'll say stub connected. Just like before. We'll take down the adjacency and reform it, and we are now a stub router here in the configuration, and that works very similar to how the stub EIGRP feature worked before. This router R4 will not be queried. It's a great way to do query scoping in your design. And R4 will advertise to the rest of the EIGRP network its connected networks that it knows about. So I hope you've enjoyed this exploration of IPv6 EIGRP. We saw some very interesting things about the protocol's configuration in this demonstration, and I think you should be ready now to explore this wonderful protocol on your own. What if you want a high degree of control over routing in your environment? What if, for instance, you want to override the routing table and have traffic take a path that is a different path from what the routing table would like to do? We often call this traffic engineering. We could accomplish this in IPv4 using something called policy-based routing, or PBR. The great news is we have this capability in IPv6 as well, as we will see in this video on demand. When it comes to policy-based routing, we have the ability to manually configure the routing of packets. In addition to having packets take a path that they wouldn't ordinarily take through the network, with policy-based routing, we can also do classification and marking as well. Just like with IPv4 policy-based routing, in IPv6 we're going to get many different options for matching traffic. And based on these options for matching, we can go ahead and have many different options for setting behavior based on one of these matches. We want to go ahead and show you policy-based routing in action. So as a result, we've constructed this topology behind the scenes. Notice it's a topology that includes frame relay, and we have version 6 IP addresses configured on these interfaces throughout this 5 router topology. So we've got routers 1, 2, 3, 4, and 5. Notice, to ensure full reachability, we have configured IPv6 RIP throughout this entire topology. Let's first take a look at an example where we will manipulate traffic based on where that traffic is from. So in this first attempt at policy-based routing in this topology, we want to go ahead and we want to examine the source of traffic. And if the source of traffic is from a particular location, we want the traffic to take a different path than what would ordinarily be taken in the routing table. Here in our topology, you can see the green path. This is how traffic is going to flow if allowed to flow normally from R5 to R2. Notice we've drawn in a red path. This is the traffic engineering path, if you will, that we want traffic to take. If the traffic is from a particular source, we're going to have it rerouted through R3 with policy-based routing. Well, where are we going to do the policy-based routing in this example? Well, we're going to go ahead and configure policy-based routing on R1. Notice this is the router that the traffic would take the path through under either circumstance. Specifically, this fast Ethernet 0/0.15 subinterface is the interface where we are interested in putting policy-based routing. We're going to analyze packets that come in this interface, and if given certain criteria, we're going to send them out either towards R2 or towards R3. So let's go ahead and get started. We'll go to R1 and we'll enter global configuration mode, and then I'm going to create a route map. We do our policy-based routing inside of a route map. So here are the commands that I'm going to use in this configuration example. I'm going to create a route map called policy-based routing _ source _ address. And this is a permit 10 entry in this route map. I am then going to match on an IPv6 address as referenced in an access list called source _ 105. So this is how easy it is to match based upon an IPv6 access list. We can just say match IPv6 address. So we're looking for a certain address. If there is a match, notice this is a permit route map entry. If there is a match, we are going to do whatever it says to do in the set command. And in the set command, we're going to set the IPv6 next hop address to be 123.3. So you can see that we are going to send traffic to R3 if it matches this particular source address. Speaking of the source address, by the way, let's go ahead and configure that now. The source address we know is going to be defined in an access list named source _ 105. So we'll go ahead and we'll create that access list right now. We create an IPv6 named access list called source 105, and notice we are permitting the IPv6 address, oh look at this, if it is in the 105 network. Okay, that's its source address. Its destination address is going to anywhere. So if its source address is in the 105 network, it is going to match this route map condition. And the next hop address will be set to 123.3. Now, if we look up here in the topology diagram, the only traffic that we're going to have sourced from R5 that matches this criteria is loopback 105 traffic. So notice, if the traffic is coming from this loopback, it will be policy-based routed, we hope, through router 3. If it's coming from, let's say, the fast Ethernet interface of R5, that's where traffic would normally be sourced from, it's going to be routed as normal per the routing table, as you can see in the green path highlighted on screen for us here. So now we're ready to go ahead and apply this policy-based routing. So we'll go ahead and we'll enter the Fast Ethernet interface. And on the Fast Ethernet interface, we are going to configure the policy-based routing with the IPv6 policy route map command. We reference that route map that we created earlier in this IPv6 policy syntax. Notice, very simple to put the command that's required on the interface to get policy-based routing working. Now, something that I want to do right now is I want to go ahead and on this router, we're going to go ahead and do debug IPv6 policy. So we are going to turn on policy-based routing debugging for IPv6 on R1. This is a great way to test, isn't it? Okay, now if I go over to R5 and I go ahead and I initiate some ping traffic, we can test policy-based routing. The first thing I'm going to do is I'm going to go ahead and I'm going to ping this other side of R2 from R5. Now notice, where's the traffic going to be sourced from? Yeah, you better believe it. With this ping statement, the traffic's going to be sourced from 15.5. And as a result, it should follow a normal path to get to the other side of R2. We can notice the round trip min, average, and max values here. And we could also obviously do a trace of this to see how the traffic flowed. But I'm pretty convinced right now that because this source address was what it was, normal traffic forwarding was carried out. Now, if I were to say ping 123::2, and I were to say source loopback 105, if I were to source these ping packets from the loopback interface, now we should be policy-based routing. I've got a pretty good clue that we were, because look at the min, average, max values for the pings. Look at this. We've nearly quadrupled some of these values. Looks like we are taking a longer path to get to that destination. The ultimate proof here would be a trace, or remember what we did on R1. We turned on IPv6 policy-based route debugs, and sure enough, look at what happened here. We had a match on the source address, and as a result, we had a setting of the next hop to 123.3 out serial 1/0, and we did indeed policy route traffic via that interface. So here we can see the entries for the matched traffic, and we can see policy-based routing in effect. I'm going to go ahead and turn off debugging there, but notice how the debug is a very, very powerful proof that our configuration is functioning successfully. Now, when you look at the configuration of R1, if I do a show run, and let me include IPv6, and that should show us, actually what I want to do is, if we look at, let's do this, let's do a show route map. If we look at our route map, you will notice that we again matched on traffic sourced from loopback 105, and that would trigger the policy-based routing. And as far as our set action, we set the next hop to 123.3. The question I have for you is, could we have set the next hop value to the link local address? Could we have done a next hop of the link local address? And the answer is no, you cannot. Watch out for that. It clearly tells us in the documentation that we can set the next hop to a global unicast address, and they definitely meant that. So this is a case, interestingly enough, where link local addressing is not going to work. We want to make sure we are referencing the global unicast address when setting next hop. Now, there is literature on policy-based routing available for you in the technical library at netmasterclass.com, but I do want to talk about one particular issue right now. And by the way, that documentation that goes along with this topic that's in the library, great examples up there of other policy-based routing tricks. We show you an example of policy-based routing based on the destination address, based on the source and the destination address, all kinds of great examples for policy-based routing. There's lots and lots of different things you can experiment with policy-based routing. But one topic that I'd like to leave you with at this point is I'd like to leave you with a thought of what about traffic sourced from the router. In this example, we went ahead and we did policy-based routing on R1 for traffic passing through R1. But what about the case if R1 is generating the traffic? Or what about the case if R5 is actually generating the traffic? Can we do policy-based routing on traffic that we are generating? Well, we sure can. Let's go over to R5 and let's see an example of this. On R5, I'm going to go ahead and I'm going to try writing one of these policy-based routing route maps. I'm going to say route map, and we need to give it a name. Let's say local-PBR. And then what's next in our route map? Ah, yes, a permit statement and a line number. So we're going to create a route map here called local-PBR permit 10, and I want to match on an IPv6 address. I'll match on an IPv6 address, and this route map that we will create will be loop 105 will be its name. We better say loop interface 105. We obviously can't have that name be a keyword. We don't want to do that. Okay, match IPv6 address loop int 105, and then what are we going to do? And let's see, this demonstration's actually going to be much better on R1, isn't it? Yeah, because on R1 we have two different paths that I can manipulate. Again, we can have R1 forward things to R3 or R2. So actually, let me just quickly create this over on R1 again, where we've been creating things before. So we're going to do route map, and we are going to do local PBR. Let me get my syntax correct here. So it's route map, local PBR, and we're going to say permit 10. Alrighty, now match IPv6 address, and we'll say loop interface 101. And we're going to say set next hop, and the correct syntax here is going to be set IPv6 next hop, we can't forget. And let's go to that 123 address again. We're going to take a roundabout way to get to the destination we're trying to get to. Okay, so if we have a match on a particular address, then we are going to send traffic via that destination. Notice this example is very similar to the example that we were doing before, wasn't it? Okay, where we match on a particular IPv6 source address. Okay? But this time, what we're trying to do is we're trying to make the source address we're matching on a loopback interface on R1. This is testing policy-based routing for traffic we generate, not traffic that's coming through us. If I do show IPv6 interface brief, I think we'll see, yes, good, we have a loopback 101 interface. And this interface has an address of 101 on it. So here's what I'll do for the access list. We're going to say IPv6 access list, and that was loop int 101. Let's make sure that matches with what we called it. Yep, loop int 101, perfect. And we're going to say permit IPv6, and it was the 101 network. So the source of the traffic is going to be the 101 network. Okay? Now, that's the route map. Where do we apply it? Again, an interface isn't going to be appropriate here, is it? Because we are not working on traffic that's moving through the router. We're working on traffic that is originating from this router, R1. So where we actually put the appropriate command is in global configuration mode. We say IPv6 local policy, and then we go ahead and we reference the route map that we created for locally sourced traffic. Mine's local-PBR. And that's it. Oh, IPv6 local policy route map. It wanted me to specify the word route map and then the name we gave it. Context-sensitive help can really get you out of trouble right there. I was having trouble with this command, and the context-sensitive help saved me, and obviously you want to use that technique in the lab exam. So here in global configuration mode, we set the local policy for locally generated traffic to be local-PBR. Now, testing could be just like before, by the way. We can do debug IPv6 policy. And as far as a ping goes, if I ping on R1 to R2, let's ping to the 12 network, we see it functions great. There was no policy-based routing. No policy-based routing because we are sourcing the traffic from the serial 1/0 interface and sending it directly to R2. But if I were to do that same ping and I were to say source loopback 101, we should see, aha, look at this, local policy being implemented. Let's scroll up here and see what happened. Ooh, we had a local policy for locally sourced traffic, and we did indeed match on the appropriate source address, so a new next hop was set. And this happened a bunch of times for each of the ping packets. So notice, we have plenty of flexibility with IPv6 policy-based routing. We can manipulate traffic that is coming through the router. We can also manipulate traffic that is originating from the router. Certainly hope you enjoyed this presentation on IPv6 policy-based routing. And again, there is literature available in the technical library which gives you many, many more examples if you are interested. Well, I hope you're ready to have some real fun with IPv6 because we are going to start a series of video on demands here regarding IPv6 redistribution. We're going to start with our friendly little neighborhood protocol, RIP Next Generation. RIPv6 and RIPv4 are different, as you know, in that RIPv6 is a per interface configuration where we configure RIP version 4 under the process. But that's not all the differences that exist in these two protocols, as we're going to see in this really fascinating, at least I find all this fun and fascinating, I hope you do too. In this video on demand, we're really going to see some very interesting things about how this protocol operates. For example, if we have two interfaces on the same subnet, but in different RIP instances, they're going to actually accept updates from each other as long as they use the same multicast group and the same port number, as would typically be the case. So we're going to see some really fascinating things, trust me, about redistribution of RIP next generation in this video on demand. Let's take a look at the topology that we'll be working with. Notice we're going to be experimenting with redistribution between R1, R2, and R3 in this case. We're going to be working with the redistribute connected command. We're going to be looking at different RIP processes. Notice R1, R2 is one of our processes. R1, R3 is another process. Well, let's get started. The first thing we should do is verify connectivity. So let me go ahead and ping the 1232 address from R1. Let's make sure we have good connectivity there. That's from R1 to R2. That checked out. Now let's go ahead and do this for the 123.3 or .3 I should say router interface. That's R3. That's perfect. So we just verified full connectivity on the fast Ethernet segment that exists between R1, R2, and R3. All right, on R1, let's go ahead and create our IPv6 router RIP process, and we're going to use R1, R2, and I better be in global configuration mode when I issue this command, or we're going to get an error. So let me go ahead and try config T, and then let's go ahead and paste that command in there. IPv6 router RIP R1, R3 on R1. In fact, I said R1, R2. We need that to be R1, R3. So on this fast Ethernet 0/0 interface of R1, we're going to create the R1, R3 process. How we do this, we've just created the process, but then to enable it on an interface, we're of course going to go fast Ethernet 0/0 123, and we're going to say IPv6 RIP R1, R3 enable. And now we've truly got RIP running on that particular interface. Now what we'll do is we'll slide over to R2. And on R2 we're going to say IPv6 router RIP R1, R2. Notice this is a different routing process. There, I did it again. This is a different routing process than what we set on R1. So we set R1, R3 on R1. Here on R2 we're doing R1, R2. Now let's go into the appropriate interface, and that's fast 0/0.123, and we'll say IPv6 RIP R1, R2 enable. Okay, so let's go ahead now and go to R2 and say do debug IPv6 RIP. And then we'll go into the IPv6, and here we're already seeing updates going out, but watch this. We're going to go into the IPv6 router RIP R1, R2 process, and we are going to say redistribute connected. And we're going to redistribute our connected interfaces. Notice that we are sending the connected interfaces to FF02::9, the default multicast destination for RIP. Notice the metric is set to 1 by default for these connected interfaces. And we can actually see them there. It's 102, 123, 24 that we are sending out as a result of the redistribute connected command. So by default, redistribute connected will cause RIP to generate an update for all the connected prefixes with a metric of 1. We see that the destination is the default multicast address, and the destination default port is port 521. Now, if we were to take a look at R1, and we go up to R1 and we do a show IPv6 route RIP, we see, look at this. We are actually learning updates from R2. And that is amazing. They're sharing information. This R1 is configured for R1, R3. This R2 is configured for R1, R2. And the updates are happily being shared, even though they are in the different RIP processes. Let's go ahead now and configure R3. We'll say IPv6 router RIP, and this will be R1, R3, and then we'll go into the appropriate fast Ethernet interface, and we will say IPv6 RIP R1, R3 enable. Okay. R3 should be getting these updates as well, shouldn't it? Do show IPv6 route RIP. And it is indeed getting the updates as well. So now, what if we wanted to separate these RIP domains? How could we do that? How could we separate the RIP domains? Well, right here in R3, let me say IPv6 router RIP R1, R3, and go into the RIP routing process, and let me say port 1013 and multicast address FF02::9. What are we doing here? We just went to R3's RIP process and we said, you know what? You're not going to use the default port anymore. You're going to use a port of 1013. You're still going to use the same multicast address for RIP, but you are going to use a different port. So do you see how we can force the separation of these processes? On R1, I'm going to go in and I'm going to say IPv6 router RIP R1 R3, and you betcha what we're going to do here, we are going to set the port to match. That'd be 1013 multicast address. By the way, that's what MU stands for, multicast group, FF02::9. So we set it to match here on R1. Now, if we do clear IPv6 RIP R1 R3, let me actually copy this command. Because we want to do it on R3 as well. If we clear the RIP processes on these two devices and we look at their routing tables, what we are going to find is, let's go over and do it on R1 as an example. Do show IPv6 route RIP. We're going to see no more routes. These devices are no longer listening to R2. R1 and R3 are in this R1, R3 process now with a unique port assignment, and they are not listening to the updates from R2 anymore. So now what we get to practice with is having R1 do mutual redistribution. We can set up mutual redistribution between R1, R2 and R1, R3 processes on R1. So let's go ahead and try it. In router configuration mode for R1, R3, which it looks like we are still in, perfect, we are going to do redistribute RIP R1, R2. So we're going to take the R1, R2 process and redistribute it into R1, R3. Then we're going to turn right around and say IPv6 router RIP R1, R2, and we are going to redistribute RIP R1, R3. So we are doing mutual redistribution now of those two areas that we separated, or I should say instances that we separated. Let's go over to R3 and see if this redistribution has worked. Show IPv6 route RIP. Not yet. This could take a moment, right, for the redistribution to work on R1. RIP is not the fastest of converging protocols by any means. We should have routes show up on R3 if we've done this correctly. Take a look at R1, make sure I've done everything correctly here. We were in router. Oh no, look at that now. I was actually in R1, R3. Let's see what we were left with for configuration on this device. Let me do a show run. Let me see. Okay, IPv6 router RIP R1, R3, redistribute RIP R1, R2. That looks good. Uh-oh. And no, we did not do this correctly. What I need to do is I need to say IPv6 router RIP R1, R2, redistribute RIP R1, R3. And now we should be in good shape. Let's rerun the verification command on R3. Again, this might take some time, but we should see the mutual redistribution taking place. That is, of course, if I remember to take R1's interface and place it in R1, R2. That would help. Let's do that. Let's say interface fast Ethernet 0/0123 IPv6 RIP R1, R2 enable. And now R1 does indeed have both RIP processes on it and is indeed redistributing between the two. So if we go over to R3 and we run our show verification command, there we go. We have the addresses showing up now. What I had forgotten to do there was take this fast Ethernet interface and put it in both RIP routing processes, the two we separated with the port number assignment, and then once I put it in both, we could redistribute in both directions on R1 and have the full reachability again. Now, let's try a configuration where we go to R3, and as you can see from our documentation here, we want this interface to come in to R1, R3 with a metric of 16. We want this interface to come in with a metric of 5. And actually, what we are going to want here from R1's perspective is a 6, and we want unreachable, thus 16, for this particular link. Let's see if we can get this configured. On R3, we're going to make the following configuration. And again, you're going to notice this is very similar to a RIP configuration like we might make in a v4 environment. On R3, I'm going to say IPv6 router RIP R1, R3. And then we're going to say redistribute connected, and we're going to reference a route map. This route map we're going to reference is the connected prefix route map. Let's go ahead and create that route map now. Our first route map statement is going to be to go ahead and match an IPv6 address, and that's going to be connected prefix 34, and set the metric to 15. We're setting the metric to 15 because we know it will be incremented as it's passed to R1, and that'll make it unreachable at 16. Okay, and we're going to match the correct prefix with an access list. Our next route map statement, we're going to go ahead and match the other connected interface that we are interested in manipulating. We're going to match it, just because we can, using a prefix list. So let's match on a prefix list, and let's set the metric there to 5. That'll get incremented to a 6, and that is what we want to demonstrate. Now, let me go ahead and create the access lists and the prefix lists that are referenced in this route map. For the prefix list, we're going to make sure we permit the 103 address. That's the loopback 103. And for the access list, we're going to go ahead and permit the 34 address. That is the serial link address. So if we do a debug on R3, do debug IPv6 RIP, what we should see in the updates that are going out is these connected interfaces that we've specified in the route map, and we should see that their metrics are set appropriately. And the metrics we should expect to see are 5 and 15 on these particular updates. And look at that, it's working perfectly. 103, the 103 prefix does indeed have the metric of 5 as it's being advertised, and the 34 prefix does indeed have a metric of 15. If you go up to R1 and check the routing table, we do a, how about a show IPv6 route RIP. Sure enough, we see it is learning the 103 network with a metric of 6. Okay, it was introduced as 5, it's 6 up here on R1, and sure enough, no reference here of the 34 network due to the incremented metric, and it increments to 16, and it is unreachable. Now, let's go ahead and do some further experimentation here that I think you'll find fascinating. On R1, let's go ahead and create a loopback 101 and put it in R1, R2. You would expect this to show up on R2 and on R3 via redistribution that's going on R1, but let's see if it actually happens. So on R1, we're going to say interface loopback 101 IPv6 RIP R1, R2 enable, and that should do it. That should do it. If we go over to R2 and we look for this, do show IPv6 route RIP, we see that it's showing up with a metric of 2. Great. Let me do a do you all to stop the debugging there. Now, if we go over to R3 and we show IPv6 route RIP, no loopback 101. Why is the 101 prefix being advertised to R2 and not R3? Well, it's because IPv6 dynamic routing protocols like RIP, OSPF, ISIS, and EIGRP do not redistribute networks that are also connected on the redistribution router. We have to use either the redistribute connected or the include connected keyword on the redistribute statement. Imagine that. So even though we're redistributing between R1, R2, and R1, R3 on this router, we're not getting this connected interface into the R1, R3 redistribution because that is simply not how the protocol works. What could we do to fix it? Well, we could go to R1 and we could go into the IPv6 router RIP R1, R3 process, and we could say redistribute RIP R1, R2 like we did before, but this time we're going to say include connected. So we use the include connected syntax when we're redistributing into R1, R3. If we go now and we look over in R3 and we run our show command, we see the 101 interface is showing up beautifully. So it leads us to an important final question here. What is the difference between redistribute and then the include connected and the redistribute connected? Well, the difference is we use the redistribute include connected statement when you want to redistribute the connected networks that are also covered by the protocol you are redistributing from. So this was a perfect candidate for the include connected syntax. We want these interfaces, these prefixes to be redistributed. Oh yeah, and include this one because it's part of R1, R2. If you were to add another interface here and do the include connected, it wouldn't go in. So the redistribute connected as opposed to the include connected is much broader, isn't it? If we say redistribute connected, we're going to get every single connected interface going in. The include connected, in this case, is only going to encompass R1, R2. We can prove this, obviously, and I can do it real quickly. We can say interface loopback 200, and I can say IPv6 address 2001:1:1/64. If you do a show IPv6 route, you're going to see that this is a connected interface, but guess what? It's never going to show up on R3's RIP table. It never shows up on R3's RIP table because while it is indeed connected, we used the include connected syntax, and this interface is not part of R1, R2. As a matter of fact, if I were to go in, this is so much fun, I can't stop. If I were to go in and say, okay, interface loopback 200, you are covered as part of the RIP R1, R2. If I say IPv6 RIP R1, R2 enable, what now is going to happen, thanks to the include connected syntax, is it should show up on R3, and it does. So that is the key difference between include connected and simply redistribute connected. Well, I hope you've enjoyed this video on demand as much as I have, and I hope you'll be joining us for future video on demands that explore redistribution farther with different protocols. It's time now to take a look at another example of IPv6 redistribution. This time we'll take a look at RIP Next Generation and OSPF for IPv6, and we'll look at issues and configuration aspects that you should be aware of when it comes to redistributing these protocols together. Now, if you went through the earlier video on demand regarding RIP redistribution, you're familiar with the RIP portion of this topology. Notice we have the R1, R2 process and the R1, R3 RIP process that we have built. What we have done behind the scenes is we have added the OSPF topologies that you see before you. Notice we have an OSPF area 102. As a matter of fact, I'm about to create that right now for you live. But what I did behind the scenes was tested connectivity between R2, R3, and R4, and I also quickly built the OSPF area zeros. Notice for process ID 1 versus process ID 2. So this topology has been built with the exception of, as I said, area 102. Let's go ahead and build that right now. I'm just going to go to R2, and I'm going to go ahead and I'm going to indicate that we want to take interface loopback 102 and place it in area 102. Something that we can immediately begin to play with now is the fact that, just like IPv4 OSPF, the databases from the different processes here on R4 are not going to communicate. They are isolated. If we want to exchange routing information between these two OSPF process IDs, we have to redistribute it. So here we have advertised loopback 102 and area 102 on R2. And now what we're also going to do is go ahead and advertise loopback 103 over there on R3 as an external metric type 1. We'll tag it with a label of 3333 just to show some of the redistributed connection options, and we'll see what is happening here in our OSPF environment. So again, we're creating the area 102 here, and we're also going to redistribute this loopback into OSPF and view the results. Let's go over to R3 then, and let's do the configuration on R3. Again, we want to demonstrate just how easy it is to do configuration options for connected interfaces in OSPF, just like we would do in OSPFv3. So I'm going to go into the OSPF2 process on R3, and I'm going to redistribute connected, setting the metric type to 1, setting a tag of 3333, and specifying a route map called connected prefix to OSPF. We'll then create that route map, and we are going to match on an IPv6 prefix list. So notice this is very similar to OSPFv4 redistribution techniques. I'll then go ahead and create my prefix list, and I will indicate that we just want to redistribute the 103 loopback network. So this just single one connected interface will be redistributed into process ID 2, and notice that it'll have a tag of 3333 and be of type 1. So let's go ahead and see what we receive on R4. I'm just going to go over to the routing table of R4 here and take a look at it. We'll just go ahead and do a simple show IPv6 route OSPF in order to view the routing database there. What do we have? Well, we have inter-area OSPF route for 102. Okay, so R4 is indeed receiving the R2 loopback area 102 address, and there it is. And R4 is also receiving the 103 address, and notice it's got the tag and it has the type 1 designation. So R4 is getting both of those prefixes that we have advertised. But if we were to go to R2 or R3 and looked for OSPF information, we would find none. I know you trust me, but let me just go ahead and prove this. Let me go to, we'll pick R3, and let's run that command, show IPv6 route OSPF, and there is nothing. Nothing on R2, nothing on R3, and that's because this information is being learned by R4, but it's not being propagated out. For instance, R4 is not taking the loopback 103 from R3 and passing this along to R2 because we have the different process IDs at work, the two different databases at work. So we would need to redistribute between the processes on R4 to have this information be known throughout the topology. Alrighty, let's do that. Let's go to R4 and let's configure redistribution between the two processes. We'll simply say for OSPF1, we want to go ahead and redistribute OSPF2. And then we'll go to OSPF process 2, and the key command I want you to focus in on for this process is redistribute OSPF1. So we redistribute the second process into the first, and we redistribute the first process into the second. Now, if we were to check the OSPF database on R2 or R3, we would see they are receiving the prefixes now. On R2, I'll do a show IPv6 route OSPF, and we do indeed see the 103 prefix with a tag of 3333 that we would expect from R3 on R2. Interestingly enough, this had a metric of 1 when it was sent into process ID 2, but when we redistribute from process ID 2 into process ID 1, notice there's a resetting to the default, and now it's a type 2 metric. That is as we would expect. Remember, when we do perform this redistribution between the OSPF routing processes, they will be injected as type 2. All right, let's perform redistribute connected on R4 under the OSPF1 process only now. So let's go to R4. We know we have this loopback 104, and what we're going to do is we're going to go ahead and say redistribute connected. Let's give this a try. Additional commands here that are kind of beyond the point of the exercise that I just grabbed from my finished configurations. Obviously, what you're zeroing in on here is that we're going into the RIP R1, R3 process, and we're not only doing the redistribute connected we did earlier, that's not the point, but we're redistributing OSPF with the process ID of 2. As you look at our OSPF2 configuration, notice the point of the exercise here is redistribute RIP R1, R3, include connected. Okay, we just ran into a problem, and let me show you what we just ran into. If we go to R1, and R1 we do a show IPv6 route RIP, we are not going to see any of the OSPF networks. What in the world happened? We see on R1 that we've got the RIP learned information, but there should be a lot more RIP routes here, all of those networks that are in the OSPF domain, and they are not showing up. What's happening is we did not set the initial metric. So sure enough, the OSPF routes are injected into RIP with a metric value of 16. We could have actually seen this with debug output, but that's indeed what's going on. So to fix this, what we need to do is we need to go in and reset the redistribution on R2 and R3. We need to go in and say, okay, look, when we're bringing in the OSPF routes, go ahead and use an initial metric value of 1 as opposed to 16. So the routes will actually appear on R1. So I will redo the RIP, the OSPF redistribution into RIP, setting the default metric, and that causes another potential problem here to be fixed.
Look at this. If we rerun this command now, and that's show IPv6 route RIP, we see, once we set the seed metric, which RIP requires, we are getting all of the OSPF prefixes up there. Well, let's go ahead and try to ping between the farthest loopback networks, 101 and 104. And let's see if we have full-blown connectivity now in this topology. So I'm going to go ahead to R4, and I'm going to say, let's ping 101::1 from 104::1. And we met with success. So that is a good sign. Now, let's go ahead and take a look at the routing table entries. For instance, on R4, let's go ahead and do a show IPv6 route, and let's specifically look for a section involving the 101 and the 104 prefixes. And we can see that 104 is a connected network. That makes sense. And the 101 is learned via OSPF as external. By the way, you would learn of this prefix from R2 or R3, depending on which first became the redistributing router. It looks like in our particular case here, it was R2 that is the first redistributing router. Okay, here's a question for you. Is R3 going to have the 101 prefix learned via RIP? We would want it to, wouldn't we? We would want R3 to have the 101 prefix as learned by RIP. But that is not what's going to happen. OSPF will win out on R3 due to administrative distance. So if we go to R3 and we look at a section of the routing table, we are going to see that indeed, if you look at 101, we're going to go through R4 to get there. We have suboptimal forwarding now between R3 and R1 as a result of administrative distance. We can obviously prove this with a trace. I've got all the proof I need here, I think, but let me just do this real quick. Let me go ahead and do a trace to 101::1, and sure enough, we take a roundabout way to get there due to administrative distance. We go through R4 and R2 and then up to R1 from R3. We'll fix this in a moment, but we've got an even bigger problem on our hands. Everything looks like it's fine in this network and stable. We have some suboptimal forwarding, but that's okay. At least the network works. We've already pinged successfully from the farthest point to the farthest point. But the issue is sometimes it takes some instability to demonstrate problems. Here's what we're going to do. We're going to go ahead and we're going to turn on a pretty safe debug IPv6 routing. We love this command when we're doing redistribution, debug IPv6 routing, and on R3, debug IPv6 routing. Now what I'm going to do is on R4, I'm going to go to the loopback 104 and I'm going to shut it down. See, everything appeared fine with this loopback interface up, but with it shut down, we just created some major issues. Look at this. On R1, the 104 gets deleted, but then it gets added back to the routing table from RIP with a next hop of, in this case on R1, R2. So we down this network and it was removed from OSPF, but now R1 says, okay, I'll just get to it by going through R2. R2 does a similar thing. It deletes it and it puts it right back. And how does it think it can get there? Look, by going directly to R4. As crazy as it might seem, look at this. If we go to R4, where we just down the interface, and we do a look at the routing table there, a portion of the routing table for the 104 network, you just won't believe this one. R4 says, I can get to the 104 network, and it's through R3. We have a loop. So we were okay when things were stable, but in this case, downing an interface caused the route feedback loop issue to rear its head. Amazing. Look at this trace from 104 to its own 104 prefix that we just downed. So what we needed to happen here was this prefix to be deleted from all these databases, obviously, and not re-implemented with a new next hop. Amazing. The loop is formed because when the 104 network is up, it's redistributed into OSPF and is advertised to R2 and R3 as an OSPF E2 route. R2 and R3 then redistribute it into RIP and send updates to R1. R1 sends these updates back to R2 and R3. With the loop back up, everything's fine. R2 and R3 don't accept the RIP learned information because of administrative distance. But when we place 104 in the down state, R4 generates max age LSAs telling R2 and R3 to delete the prefix learned from R4. They do that. R2 and R3 delete it, but then they install the backup prefix learned from R1. We then redistribute that back into OSPF. So this is just an amazing example of a route feedback issue. R2 and R3 aren't supposed to learn the OSPF generated prefixes from the RIP domain and vice versa. That's really the issue. You see, these OSPF prefixes, for example, are being injected into RIP, and then they're being taught back to these routers as RIP routes. So we need to stop this kind of route feedback. For example, just think about it. When we distribute RIP into OSPF, we only want the native RIP prefixes to go in there. We don't want this OSPF learn stuff to cycle back around. It just makes good logical sense. As a matter of fact, to help you with this concept, here's a diagram. It's kind of just reminding you, okay, look, we want to send the RIP learned prefixes into OSPF, and we want to block the OSPF learned prefixes from cycling back around. When we make the configuration to fix this, then everything is wonderful. Let me show you the fix. We'll go to the loopback 104 interface, by the way, and we will no shut it. And again, when we no shut it, we have full reachability again. We don't have the loop. So we're in a non-loop condition right now, and what we want to do is implement the filtering, the correct filtering, and then go ahead and see if we still have the problem when we shut down the interface. So I'm going to do IPv6 router RIP R1, R2, and we are going to do the redistribution this time, but with a route map. And the route map is going to be called RIP to OSPF. We're going to redistribute into R1, R3, but with a route map. So notice we are creating these route maps called RIP to OSPF, and they are going to permit the specific prefixes that we are interested in redistributing and denying all others. So we want to make sure we block those prefixes that we are not interested in cycling back around. And we can do this with route maps that limit the redistribution. Here you can see, for instance, we create the a prefix list called RIPnative, and we integrate this into the RIP to OSPF route map. So pretty cool. We can use route maps to ensure we have the correct filters in place so we don't get into this route feedback situation that you saw right before your eyes. We're going to do the points of our redistribution on R1, R2, and R3. The route map on R2 is going to block RIP native prefixes from OSPF going back into RIP. On R3, we're going to do the same thing. Again, blocking the RIP native prefixes from OSPF that go back into RIP. I'll go and apply the appropriate configuration to R3. And we'll show you it. It's a similar configuration to R2. I'm going to go into the R1, R3 RIP process. And I'm going to do the redistribution, this time referencing a route map called OSPF2 RIP. And this OSPF2 RIP route map will deny the RIP native prefixes, and it will allow all other prefixes. So again, the key is to deny those prefixes being learned back from OSPF. And we can do this with a simple route map and prefix list. Once again, notice the route map is called OSPF to RIP. The prefix list is called RIP native, and the RIP native is going to single out those prefixes we're worried about, those RIP native prefixes we're worried about, and then we deny those in the redistribution. And then our route map ends with a permit statement that will catch any other routes dynamically. Now what we need to do is we need to clear the IPv6 routing table. Clear IPv6 route asterisk. We don't want any ghost entries in the routing tables. Specifically, I'm worried about RIP entries that have not aged out, that are not going to get caught by our route map redistribution statements. So at this point, we'll make sure we clear the IPv6 routing tables. And just one more. We'll do that on R1, R2, and R3. And now we will go to R4. With the routing tables cleared, we know there are no RIP routes that haven't aged out or anything like that. With the routing tables cleared, we now know that our filters should have taken effect, and now we can go to the loopback 104 interface and we can shut it down. When we did this before, we met with kind of disastrous results. What's going to happen now? If we go to R1, R2, or R3, we see that we are in great shape. Look at this. The route was deleted from the table, and it was not added back. As a matter of fact, if we go to R4, remember one of the issues we had on R4 was that it had a route for the downed interface. Now, of course, it does not. That is gone. So the routing loop is no longer, thanks to the proper filtering. We still have one problem in this topology, and that means it's that suboptimal path. The suboptimal path is because either R2 or R3 in our scenario, and let me go back to the previous graphic here. The suboptimal path occurs because either R2 or R3 end up becoming an ASBR router for the 101 prefix, and the other, either R2 or R3, depending on which happened first, will be the receiver of the E2 prefix, and this forces one router or the other to purge the RIP learned prefix. So it ends up being that we have to go all through the OSPF area to get to the 101 interface. we can configure administrative distance to make sure that RIP native prefixes are preferred on the RIP routers. So this will fix any suboptimal path situation we have. So on R2, I will go in and I will say IPv6 router RIP R1, R2 and change the distance to 109, and that should do it. Actually, we'd have to do this on R3 as well, wouldn't we? So let's go over to R3 and change the administrative distance. Again, R1, R3, and a distance of 109. Now, on R3, we can trace the path as we did earlier, and it is taking the perfectly efficient path through the RIP network after our administrative distance manipulation. The last thing I would want to do in a scenario like this would be to test for full reachability. And as you know, we can test for full reachability with a script, with what we call a tickle script. Again, this is a wonderful idea to test for reachability, and you would do this test on all of your routers. This is going to automate the pinging from your router to all of these addresses. And we can see, boy, we've fixed the loop condition, we've fixed the suboptimal path, and we've achieved full reachability. You can get yourself really scared when you do this test too. Look at right there, I couldn't get to the 104 prefix, but that's expected because we downed the 104 prefix. So that interface doesn't exist right now, and that's why we can't get there. And boy, that would remind us that we need to go and we need to up that interface. Well, I hope you've enjoyed this presentation on RIPng and OSPF redistribution. And we've got more video on demands for you on the fascinating topic of redistribution. We hope you'll join us for those. Let's take a look at redistribution again. This time, let's go ahead and take a look at RIP Next Generation in conjunction with OSPF, in conjunction with BGP regarding redistribution. Here's a look at the topology. Notice we'll go ahead and we'll run RIP R1, R2 on R2 between R1, and then we'll run BGP AS13 between R1 and R3, and then OSPF between R3 and R4. Our goal here will be to have full universal connectivity when we are done. Let's begin this configuration then, and let's go ahead and start out on R1. What we're going to do on R1 is we're going to go and we are going to configure, hey, we can't forget this command, IPv6 unicast routing, and then we'll go ahead and enable the R1, R2 RIP process on the serial 1/0 interface. Let's go ahead and on R2 configure the R1, R2 process on the appropriate interfaces over there as well. So I'll just skip over to R2 now, and I will make the appropriate configurations. Notice we can't forget about the IPv6 unicast routing command. We're then going to go into the loopback 102 interface and enable IPv6 RIP with the command IPv6 RIP R1, R2 enable. We're then going to go to the serial 1/0 interface, and we're going to use the IPv6 RIP R1, R2 enable command there as well to enable the RIP routing protocol. So there we have it, R1 and R2 configured with IPv6 RIP. Very simple, and we saw these configurations in the appropriate video on demand for the RIP Next Generation protocol. We're ready to verify this configuration. Obviously, a quick verification, quick and easy, is to go over to R1 and go ahead and do a show IPv6 route, and specifically ask to see the RIP routes from the routing table. Notice when I do this, I can see we have the 102 prefix being learned on R1, and that's perfect. That is the loopback interface over on R2. So we are learning about that remote network properly from the RIP routing process. Now let's go ahead and configure OSPF on R4. These routers that we're using do not have any IPv4 addresses, so as we learned in the OSPFv3 video on demand, we are going to have to set router IDs manually due to the lack of IPv4 addresses. We'll go ahead and begin the configuration right on R4, as I said, and we will configure OSPF over here. Can't forget the IPv6 unicast routing command. Then we'll go into the loopback 104 interface and we will enable RIP for area 0 with the IPv6 OSPF1 area 0 command. On serial 1/0 we'll use that same command to enable OSPF on that interface. And then finally, like we said, and we see a console message about it, we'll have to configure the router ID manually, and that is done under the OSPF process for IPv6, OSPF that is, and that's simply the router ID command, and we'll use a router ID here of 4.4.4.4. Alright, we have a similar configuration to make on R3, don't we? We are going to enable OSPF properly on R3. Very simple for us to do. And it's just going to involve the IPv6 OSPF area command under the appropriate interface. In this case on R3, that's going to be serial 1/1. And again, we'll set the router ID manually under the OSPF IPv6 routing process with the command router ID. Once we have made the configuration between R3 and R4, we want to verify our configuration, of course. Let's make sure we have full adjacency between R1 and R3. I'll just stay right here on R3, and I will say show IPv6 OSPF neighbors, and we'll check the neighborship. So far, nothing. Oh, but look at that. Just as I spoke it, we had the full adjacency be established between R3 and R4. As a matter of fact, we should be learning of the remote loopback network via OSPF now. So if I do a show IPv6 route OSPF, we can see that we are indeed learning of that remote network properly via OSPF. Well, now it's time for us to configure BGP between R1 and R3. So let's go ahead and make that configuration. Once again, we have to realize that because we have no v4 addressing in place, we are going to have to manually configure router IDs. So first, we'll go over to R1. We will configure the BGP process 13. We'll manually configure the BGP router ID, and then we will use our neighbor statement. In this case, it's going to neighbor to R3 at the 13:3 address. We'll then go in and create our IPv6 address family, and we will activate that 13.3 neighbor, and we will specify that we want to go ahead and advertise a network using the network statement. The network that we are going to advertise in this case is our loopback 101 network of 101. So we've established this end of the BGP configuration, and notice we are advertising a network. Now we'll just go over to R3 and we will do the R3 side of the configuration. It's going to be kind of the mirror image. The only difference is we're going to be advertising a different network on R3, of course. We'll be advertising the loopback 103 address on R3. So let's go ahead and make that configuration now. On R3, we go into the BGP process, we manually configure the router ID, we set up our neighbor statement, we turn off automatic summarization as a best practice. We then go in and we create our IPv6 address family, we activate the neighbor, and then we're going to advertise our 103 network on R3. Now, once we have finished this configuration, we're ready to verify. Lots and lots of verification steps that we could do. We showed you full verifications in the BGP video on demand. One of my favorites to do, very simple, we'll go back over to R1 and we will simply say, okay, let's try show IPv6. It's actually show BGP. I can see the neighborship just came up, by the way. That's good news. Show BGP IPv6 unicast summary. And this is going to tell us that, yes, indeed, we are neighboring with 13.3. And look at this, we have received a prefix. So that's looking real good. As a matter of fact, I can do a show IPv6 route BGP, and we can see that we are indeed installing the 103 prefix from R3 in the routing table of R1, and that is indeed a BGP learned route. Well, now let's do some redistribution. After all, that was the whole point of this video on demand. Up to now, we've just reviewed the configurations of these various v6 routing protocols. Let's redistribute RIP and OSPF into BGP AS13 on R1. So let's go to R1, and let's go ahead and go into the BGP process. And let's redistribute. So I'm going to say router BGP13, and I'm going to go into the IPv6 address family, and I'm going to say redistribute RIP R1, R2, and I'm going to say include connected. We would like to redistribute the 12::1 network, for example. Now, all we got to do for verification is skip down to R3. If we do a show IPv6 route BGP on R3, we should verify this redistribution. So I'm going to go down to R3 and I'm going to do that. And this is looking good. Look at this. We learn of the 12 network. We learn of the 101 network. We learn of the 102 network. Perfect. On R3, let's do our redistribution. On R3, we're going to go ahead and redistribute OSPF, aren't we? So I will say router BGP13. I'll go into the address family for IPv6, and I will issue the command redistribute OSPF1, and once again I'll use the include connected keyword. Over on R1 now we can do our verification. On R1 we'll say show IPv6 route BGP, and look at this, things look great. We've got the 34 network, the 103 network, and the 104 network from the OSPF domain. Okay, on R1 now it's time to redistribute BGP into RIP. So let's go to R1 and let's make that configuration. We'll be going into the RIP process and we'll be redistributing BGP. So I'll say IPv6 router RIP R1, R2, and then I will use my redistribute BGP command. In this case, it'll be redistribute BGP 13, include connected, and we're going to set the metric. Don't forget to set the metric, or we will have no luck with the redistribution as we've seen earlier in previous video on demands. So let's verify things now. On R2, we should be able to do a show IPv6 route RIP, and we should be able to see these redistributed prefixes from BGP, but alas, we see nothing. What is going on here? Well, by default, prefixes learned via BGP IBGP, that's Interior Border Gateway Protocol, they are not going to be redistributed into this other IGP. So, to change this default BGP behavior, we need another command. It's BGP redistribute internal. This command will allow the IBGP learned prefixes to be redistributed into the R1, R2 RIP process. Notice we don't have to worry about this issue with EBGP learned routes. So let's go ahead back to R1 then and follow up with a required command here. In R1, we're going to have to say, under the IPv6 address family, we're going to have to say BGP redistribute internal in order to have this meet with success. So I'll issue that command on R1, and then we're going to go back to R2 for our verification. Should be simple. The verification is just to go ahead and look at the RIP routes in the routing table, and there they are. We're getting them now, the 34, the 103, the 104 network, thanks to the BGP redistribute internal command. But now wait a minute. I see another issue. It is the fact that we don't have all the prefixes we would expect, do we? we see that we have the 34, the 103, and the 104 prefixes. These are the prefixes from R3 and R4, but we're not getting on R2 the prefixes that are directly connected to R1. We use the include connected syntax in our configuration. Well, sure enough, it doesn't work for BGP. We can leave it in there, that's fine, but it's not doing anything for us. What we have to do on R1 in order to make sure that we do see those particular networks is we have to use the redistribute connected command under RIP. So let's go in there and say redistribute connected. And now we'll pick up those connected interfaces on R1. Notice the previous attempt we tried was redistribute BGP 13 metric 1 include connected. The command I'm retyping for you right now. That command didn't help us. The include connected did not work in the BGP environment here. So we do have to do the redistribute connected command in this case. Wow, another gotcha that could really trip us up. So now on R2, let's go ahead and try it again. Let's do the show IPv6 route RIP. There we go. That's the complete routing table that we would expect to see. All right, it's time for us to configure the redistribution from BGP into OSPF on R3. And remember, we cannot forget the redistribute connected syntax. So we'll go over to R3 and we'll go ahead and make this configuration, including the redistribute connected, and we'll see if we can't get full routing awareness configured in this environment. Notice the configuration is simple here. We're going to go into BGP 13. We're going to go into our address family. We're going to say BGP redistribute internal. We can't forget that. We're going to go into IPv6 OSPF process. And we are going to say redistribute connected. And we're going to say redistribute BGP 13. And again, we'll just leave that include connected syntax, even though we know it's not really doing much for us in the BGP environment yet. Well, it's time for us to verify things. Let's go over to router 4. We had full awareness on R2. Now we're over on R4. Let's see if we've got full awareness there. Show IPv6 route OSPF should do the trick. And wow, look at that. That's looking great. We have all the prefixes. Our final test here for full reachability obviously could be a tickle script. That would be a really good idea. But for brevity's sake right now, let me just do a ping from 102 : or a ping to 102 : 1, and we'll source that traffic from 104 : 1. So we are pinging from R4's loopback to R2's loopback. That's from the two farthest points in the network. If we meet with success, which we do, we know we have full reachability in the topology here, and all of our redistribution has been successful. So once again, we see lots of potential pitfalls with IPv6 redistribution in this scenario, but if we just take our time, work through them, verify as we move along, it will be very manageable and we can meet with success.